Good afternoon to everyone. My name is Marco Francesco Funari. I'm a PhD student at University of Calabria. The research project that I'm going to present has been developed in collaboration with Professor Fabrizio Greco and Professor Paolo Nonetti. The title of this research, as you can see, is a cohesive finite element model based ALE formulation for Z-beam reinforced multilayered composite beam. I will show you the outline of this presentation. To start off, I will talk to you about a brief introduction of composite materials and its problem of damage. Moving on, I will talk to you about the theoretical formulation. In particular, I'm going to present the structural model and the derivation of variational equation from principle of virtual works. Then I will present the cohesive zone modeling in moving domain and the implementation of the rate-dependent effects in this loop. At the end of the theoretical formulation, I will talk to you about the Z-beam pull-out model used in this numerical analysis. Moving on, I'm going to present the numerical implementation of previous analysis in a finite element model. In particular, I'm going to present the moving mesh strategy. Afterwards, I will present the validation of the model and the advantages of this proposed model compared with other numerical models present in literature. At the end, I will talk to you about the results of a static and dynamic framework. Well, composite materials are frequently used in many engineering applications. The main properties of these materials are high stiffness, its resistance, and low weight. For these reasons, these materials are also used to reinforce the structure. However, these materials are frequently affected by interlaminar defect that can cause catastrophic failure mode. For these reasons, in literature are present more strategies to improve the lamination resistance. For example, the pinning, drifting, and the stitching. So, the structural model is based on a shear deformable beam and moving mesh interface approach. As you can see on the left of the screen, is present a generic representation of a multilayered composite beam formed by N layers, ND internal discontinuities, and reinforced in an area with Z-beam. In order to evaluate the evolution of these internal discontinuities, we have implemented a formulation based on ALE approach and cohesive zone modeling introduced only in interface region. As you can see, the variational equation of this proposed model derived from principle of virtual works. In particular, delta C is the work performed by the force generated from interface law. In particular, as you can see, the interface region is formed by a sum of two regions, omega depth and omega AT, in which in omega depth is present a nonlinear behavior, while in omega AT the perfect adhesion is defined. Whereas delta P is the work performed by the Z-beam reinforced area. As mentioned earlier, the interface region is formed by a sum of two regions. In this upper synoptic representation, you can see in a red box the omega depth region, in which the traction separation law for opening, sliding, and no contact law is defined, whereas the gray box identifies the omega AT region, in which the perfect adhesion and the no-contact law is implemented. In this box, you can see an analytic equation of the traction separation law, and in this box, you can see the crack growth function used for determining the initiation of the process of delamination. However, the process of delamination is essential of dynamic nature. For these reasons, we have implemented in the traction separation law the rate-dependent effects. In particular, with reference to this publication by Zhou et al., the assumption are that the critical stress of the materials is constant, and the critical crack opening or sliding displacement increase, producing an amplification of the dynamic fracture. In particular, as you can see in this figure, the critical stress remains constant, whereas the critical crack opening or sliding increase, producing an amplification of the dynamic fracture. Well, contrary the traction separation law, Z-pin reinforced area are simulated with a set of discrete nonlinear springs fixed to material domain. In particular, the behavior of the Z-pin is simulated with a bilinear law. The behavior of this Z-pin, of the single Z-pin, is formed by three phases. At first, the behavior of Z-pin is linear elastic and the stretching is lower than delta P0. Subsequently, a progressive damage is inverted and the critical displacement is reached delta Pc. At the end, when the value of stretching is larger than delta Pc, the Z-pin is completely damaged and thus the traction force tends to zero. Well, the structural problem is formulated by using a spatial coordinate, except for the cohesive functional that is implemented in moving coordinate. Indeed, the cohesive elements are present only in interface region. This is possible thanks to this operator Q. This operator is activated along the tightness direction of the laminate. This operator is able to map the moving mesh coordinates introduced only in the interface region with the material point of the laminate. This is very important because it is able to evaluate some variable used for determine the fracture energy used in the crack criterion growth. Well, very important is talk about the criterion of progress of the process zone. In particular, we have implemented iterative procedure formed by three phases. At first, I'm going to evaluate the fracture function at the extremities of the omega depth region. Subsequently, I'm going to search the value which set to 0 on the bonding length, this function. The correct increment of the crack position is this delta xt. This procedure is repeated for each time step. Well, now there are two possible questions. What is the correct dimension of the bonding length and where are the combinational advantages of this proposed model? Well, the answers to these questions are present in this publication by my professor and myself. In particular, we conclude that correct dimension of the omega depth region is coincident with the size of the process zone determined with one of the more empirical equations present in literature. The second question find the answer in this analysis below that represents a multi-delamination case more present in literature. As you can see, my proposed model is formed by 6,000 degrees of freedom, whereas the other model present in literature is needed of 15,000 degrees of freedom. Well, the analysis are developed with reference to the load scheme based on a double cantilever beam reinforced with Z-beam. In particular, geometrical and mechanical properties of the laminate, the properties of the cohesive interface, and the property of the single discrete nonlinear springs is determined with reference to this publication by Carti et al. And Young et al. In this simulation below, you can see the process of delamination in a static framework. As you can see in the graph, the results of the proposed model is in agreement with experimental results and other numerical model, but the computational effort is decreased. In this slide, you can see two parametric study in terms of Z-pin density and in terms of Z-pin reinforced area position. In particular, at the first parametric study is present for idealized configuration. As you can see, the behavior of the load curve is changed when the number of coulombs of Z-pin increase, and increase also the maximum load. Whereas the second parametric study is present free idealized configuration. At the first, the midpoint of the Z-pin area is on the left of the initial of the crack tip. The second, the midpoint of the Z-pin area overlapped on the initial position of the crack tip, and in the third configuration, the midpoint of the Z-pin area is on the right of the initial position of the crack tip. As you can see, the initial stiffness of the curve is dependent by the initial position of the Z-pin. The previous analyses are developed in a static framework. This second set of results are developed instead in dynamic framework. In particular, the load process is idealized as a ramp curve in which the velocity increases linearly until the time reaches value t0. After, the velocity remains constant. This result represents the resistance curve. In particular, compared with the static solution, the resistance curve in dynamic framework presents some oscillation. The crack growth is investigated also in terms of crack tip speed. In particular, as you can see, after the initiation phase, the crack tip speed increases strongly. When the crack tip reaches the Z-pin reinforced area, the crack tip speed decreases strongly. But when the Z-pin are completely broken, the crack tip speed increases strongly. To conclude, compared with existing formulation available from literature, this model presents lower computational effort and complexities in the governing equation. In particular, the combination between cohesive zone methodology and ALE formulation gives the possibility to introduce a linear interface element in a small region containing the crack tip front, whereas in the remaining one, linear Rothenstein equations are introduced to simulate perfect adhesion. The parametric study denotes that the presence of Z-pins produce notable improvements in the resistance curve. To validate, as you can see, to validate the proposed model, several comparisons are proposed with experimental and numerical results. Thanks for your attention.